When we look toward the center of our galaxy, we see billions of stars, but we also see massive stretches of empty black space. To find what's hiding in those shadows, we have to watch for a specific kind of light. Space is full of silent, wandering objects that emit no light of their own. Because they sit in darkness, we can't see them directly. But occasionally, one of these invisible objects drifts perfectly between Earth and a bright star in the background. This creates an event called gravitational microlensing. As you can see in this photograph, the gravity of that invisible middle object is so strong it actually warps the space around it. It acts like a giant magnifying lens, stretching and bending the light from the star behind it into a glowing ring. For a few weeks, that background star appears to shine with intense brightness. Astronomers hunt for these temporary flashes because they are often the only evidence we have that a rogue star or a hidden planet is drifting through the void. But there is a problem. Seeing that flash of light proves something is out there, but the brightness alone doesn't tell us what that object actually is. If you look at this split screen, the small, slow planet on the left and the massive, fast planet on the right create identical graphs. Brightness alone doesn't tell us if we're looking at a tiny, rocky world or a massive gas giant. We are left with a shadow of a world. Without an extra piece of evidence, the true size and distance of the planet remain unknown. To see why, think about making shadow puppets on a blank wall. If you want to change the size of the shadow, you have two options. You can use a bigger hand, or you can just try moving your hand closer to the lamp. If someone is only looking at the wall, they can't tell which trick you used. A giant shadow could be cast by a massive hand standing far away, or a tiny hand sitting right up against the light bulb. The telescopes recording those flashes of magnified starlight are looking at the exact same illusion. Physicists call this the degeneracy problem. Because the distance and the mass are coupled in our measurements, a telescope recording a spike in brightness can't distinguish between a small object that's nearby or a giant one sitting billions of miles further away. Mathematically breaking this illusion is the biggest obstacle to accurately mapping the undiscovered stars and planets within our galaxy. In 2024, astrophysicists Samaneh, Sarbaz, and Sohrab Rahvar published a study outlining a way to finally separate those two variables. Their solution borrows a trick from space exploration called a gravity assist. When NASA wants to send a probe into deep space, they fly it close to a planet like Jupiter. As the spacecraft whips around the planet, it steals orbital momentum, launching outward at a much higher speed. Sarbaz and Rahvar note that starlight flying past a moving star experiences this exact same slingshot effect. But light has a strict physical limit. No matter how much energy it steals from a moving star, a beam of light cannot travel faster than the universal speed limit. Since the light cannot speed up, it has to put that stolen energy somewhere else. It absorbs the extra power by shifting its frequency. As it gains energy, the actual observable color of the light changes. This color shift becomes a vital tool when we look at binary systems. A significant portion of the stars in our universe are not alone. They are locked together, orbiting around a shared center of gravity. Instead of a single object drifting quietly through space, a binary system is a swirling dance. Their constant rotation creates a moving gravitational field. When the light from a distant background star passes precisely through this spinning twin star system, it gets caught in the turbulence. This color change is incredibly small, about 1 part in a trillion. It's too subtle to see with the naked eye, but with tools that split light into a detailed rainbow, we can measure it. By measuring that exact color shift, we can calculate how fast the planet is moving. Once we have the speed, the mystery is solved, and we can finally determine the planet's true mass. To find a shift this tiny, astronomers analyze the specific color signature of a massive star like Betelgeuse, studying its light to the finest detail. Researchers test this idea using simulated data, seeing if our current sensors can catch that microscopic change in the light's frequency. To get the answer, they line up the original light signature with the one that was flung through space. They slide the patterns back and forth mathematically until the jagged peaks match up, which reveals the precise distance the light color shifted. It takes the gravity of entire star systems to create this effect, but it takes extreme microscopic precision here on Earth to observe it. By reading the color shift of a light slingshot, we turn an ambiguous guess into a clear measurement of a world across the galaxy. It is the same physics that causes an ambulance siren to change pitch as it drives past you, just applied to the scale of the entire galaxy. As our instruments get sharper, our view of these distant worlds becomes clearer. To see more of the clever physics shaping the cosmos, subscribe below, and I'll see you in the next video.